Hello students, we are going to review nitrogen compounds class exercise 2, and through this class exercise you are going to see how this topic links up some of the contents in the previous topics. Okay, so for the first questions, you were told that 4-methylphenolamine and benzoylamine are two isomers, and each of these compounds can be made from methyl benzene in two steps. So you are supposed to suggest the reagents and conditions for each of the two steps and give the structure of the intermediate compounds. Okay, so I think I will just start off by drawing out the structural formula, okay, of methylbenzene. Okay, and then of course, because it's just two steps, there must be an intermediate compound before I draw out my final products, which is 4-methylphenolamine. Okay, so I'm going to use a different color pen. Right, so starting material has a methyl group. Products has the NH2 at the 4th position, so you are probably aware that you need to introduce a nitro group at the 4th position. Why a nitro group instead of NH2? Because you know from the topic on arenes, that is topic 12, that it is not possible for you to introduce NH2 directly. So if you are going to perform electrophilic substitution, you are required to introduce NO2 first before you reduce NO2 to NH2. Okay, so because of that, I'm going to do that. So I'm just going to draw my intermediate first with the NO2. Okay, so I'm just going to introduce nitration conditions. So that will be cons nitric acid and cons sulfuric acids. Do I need to heat it at 55 degrees Celsius? That's a very common mistake. The answer is no, because that involves the formation of nitrobenzene, not 4-nitromethylbenzene. Okay, because the methyl group is electron donating, so you do not need to maintain it at 55 degrees Celsius. So you probably require a lower temperature. We'll just put RT for now. Okay, then after that, the next step, you're going to reduce the NO2. How are you going to reduce the NO2? So you're going to use a very classic condition that is introduced to you in H2. Yeah, that will be excess hydrochloric acid with tin. Okay, so I'm just going to put tin with excess con HCl. So that will be the first step. Okay. For the second step, right, I'm going to introduce sodium hydroxide. So I just going to put cold sodium hydroxide. I can just put sodium hydroxide or just put cold. The reason for introducing the sodium hydroxide is that if you notice, this particular condition is acidic in nature. So because it's acidic in nature, right, your final product is the protonated form of phenolamine. Yeah, so the reason why I want to add in sodium hydroxide is to deprotonate this in order for me to get the products that is required of me by the question, which is 4-methylphenolamine. Okay, so that's the reason for that. I think it's always good to understand the reason instead of just memorizing whatever is given to you in the lecture notes. Okay, then for route 2, we are supposed to produce benzoylamine. Okay, so again, I'm going to draw out methylbenzene. Okay, there must be an intermediate before I produce this NH2. Okay, right, so you notice that now the NH2, right, substitute one of the H here. Okay, of course it's not told to you, but you kind of like get it that there must be some form of substitution. So in order for you to perform substitution, you are probably aware that I need to convert methylbenzene into some form of halogen derivatives. So the best example is probably just convert it to a chloromethylbenzene, something like this, right? So that I can perform SN2. Yeah. So in order for me to convert to chloromethylbenzene, right, what I need here would be chlorinating condition. So basically just chlorine gas under UV. So this the first step, free radical substitution. Okay, so this is topic 10 on alkanes. Then after free radical substitution, I'm going to introduce excess ammonia. Okay, so I'm just going to put excess ammonia to perform nucleophilic substitution and then heat in Silk tube. Okay, so because of that, I'm going to perform nucleophilic substitution of ammonia as the nucleophile onto the electrophilic carbon over here. So delta plus, delta minus, and then it will kick out the chlorine. Yeah. If I'm using limited amounts of ammonia, right, I will probably end up with some form of a secondary or even a tertiary amine, which is not desirable here. Yeah, because over here I require the formation of a primary amine. Okay, yeah. So this brings us very nicely to question 2, because for question 2, right, we have compound A, C3H9N, heated with excess bromoethane. The keyword here is excess, because excess does tell you that there might be multiple rounds of substitution, and then I get ionic compound B. So this ionic compound, right, later on when they said that aqueous silver nitrate is added, right, you get a cream PBT. So it does tell you that what you are getting at the end of the day is likely to be a quaternary ammonium salt. Okay, so from here you can conclude that this is likely to be AgBr, and then this ionic compound, okay, is likely to be a quaternary ammonium salts. Okay, there are many ways to do this question, honestly. I mean, I think during tutorials I showed the class a few ways. One way is to draw out all possible compounds with the molecular formula C3H9N. Actually, there are only 3, so it's not too difficult to draw them out, or 3 or 4, depends on how you look at it. Another way is to work backwards based on the molecular form, based on the MR given to us. Okay, so we can probably adopt another strategy, different from the one I introduced in class, so that it can give the reader a fresh perspective on how we can solve this kind of question from multiple angles. So if you look at 195.9, right? I'm just going to do arithmetic here. 195.9. You know that the AR of bromine is 9.9, so I just subtract bromine off. Okay, and then over here, right, I'm going to end up with probably 116.0. So I 116.0 to kind of play around with the molecular formula of the carbon, the hydrocarbons side chain, you want to call it, or the alkyl groups bonded to the nitrogen. So 116.0, actually not too difficult to play around with, because based on this, right, you know that you probably will not be expecting a C10 or even a C9. The reason why you're not expecting a C10 or C9 is that C10, the number of carbon is 10, then the MR will be 120. So 120 is already exceeded 116. And then if it's C9, it will be 108. And then you know that that's kind of like impossible, because you have a huge degree of unsaturation. So you end up with something like C9, like H, maybe 8. Which in this kind of situation is not possible, because how do we know it's not possible? Some of you might ask, because you'll be thinking, isn't this a bit like trial and error? It's not really trial and error, because you start off with a saturated compound, right? And then when you hit it with bromoethane, right? Bromoethane is saturated as well. So it's not likely that you end up with something that's unsaturated, even if it's possible, right? Probably just 1 or 2 degree of unsaturation. But if it requires that kind of processing, right, then we need to give you more information. It can't be just like, oh, I just pump in excess bromoethane, I get an ionic compound, and then please deduce the structure of A and B. That is a bit unreasonable. So because of that, you can kind of be safe that, or it's safe to say that my final product is likely to be saturated. Okay, of course it's some guessing on my end, or even on the student's end when you're performing the exams. But these are very important skills that you probably want to come out with. Okay, and you realize that they are actually more accurate than you can think of. So right now we'll take the middle ground, perhaps a C7 system. A C7 system, we will have a MR of 84, so that will be 116.0, subtracting 84. Not to forget, I have my nitrogen, so that will be 14. Okay, so if you just do a quick calculation, we end up with 18, right? So C7H18. So this might be possible to be the alkyl groups that are bonded to the nitrogen. Okay, yeah. Then if you already decide that it is a C7 system, then what you can do is from here you look at the excess bromoethane. Okay, so if we have a bromoethane and I have a C7 system, right? That means that the number of bromoethane being added is two equivalents. Yeah, so if it's 2 equivalents of bromoethane being added, that means that to begin with, my A must be a secondary amine. I don't know if you can get this logic. Okay, so basically, right, if it is okay, so maybe I'll try to get the logic here for you. So if it's a primary amine, right, so that means that the number of bromoethane added will be 3. Yeah, because primary will become secondary, secondary become tertiary, tertiary become quaternary ammonium, right? So that will be 3. So then that means that the total number of carbon increase will be 3 plus 6, so that will be 9. So that will be 6 carbon increase. Yeah, but I have 7 here, so it can't be 9, right? So must be 7, right? Yeah. So in that case, I'm looking at secondary amine. Yeah. So the number of bromoethane being added is 2. So if it's 2, then it will be increased from 3 to 7. So that will make perfect sense, because 3 to 7, I think it kind of like fit the formula. If it's tertiary, then I'm only adding 1. Yeah, then the increase will be from 3 to 5. Yeah, then that probably wouldn't fit the molecular formula of 195.9. Yeah, so you can work on this basis and then see if you can get the answer. Yeah, so this is one strategy you can use if, let's say, you are trying to guess what it is. But of course, what we discussed in the tutorial, it's a lot easier, because what we discussed in the tutorial is simply going by brute force. Not really going by brute force, but just looking at possibility. So we have a primary amine, we have a secondary amine, and then we have a tertiary amine. Okay, then if you look at what we have over here, right? So a primary amine will need to add 3 of the C2H5. Yeah, so based on that calculation, you can easily do the calculation. Okay, so I'm just going to demonstrate once for you. So the molecular formula of A, right, is 30. Let me just do a quick calculation. So that will be 36 plus 9 plus 14. So that will be 59. Okay, it will be 59. Yeah, so if I add 3 C2H5Br, so okay, so ethyl group is 29. Okay, so this is 29. So I'm just going to add 59 plus 29. Okay, plus 29 3 times. Okay, and then I need to add 9.9 because of the bromine, and then I need to minus 2. The reason why I need to minus 2 is because in the process 2H will be lost. Okay, so you can actually do a quick calculation and you see whether this matches, because you see whether you end up with 5. So 9, 18, 27, 36, 45 minus 2 is 43. So this doesn't fit. Correct? So you end up with a 3 here, right? So it doesn't fit. Yeah, so that's what I illustrated during tutorials, right? So if it doesn't fit, then let's try another one. So let's try the secondary one. So the secondary one will be 59. Okay, I add 2 bromoethane. Okay, I add 79.9, and then I minus 1, right? Because ultimately one of the H is lost. Okay, so if I try this, 9, 18, 27, 36 minus 1, so that is 5. Okay, so I'm going to add now with probably 195.9. Yeah, so based on this, my structure of A is the secondary amine. Okay, and of course B will look like this. So this is A, and then B will take on the structure of quaternary ammonium salts with a plus here and a Br minus. So this is actually an ionic compound. Okay, yeah, so yeah, there are several strategies, different strategies you can use, but eventually you need to find your own voice. Of course, at the beginning I was showcasing a slightly different strategy that might be a little bit challenging for some of you. Yeah, so probably we can stick to the strategy that we discussed during tutorials, because that might be a little bit more straightforward. Okay, yeah, then moving on to question 3. It's a modified questions from the 2017 paper. So we have hydrogen azides used as a reagent in the Schmidt reaction. Insert an NH group into a CC adjacent to a carbonyl. Okay, so you need to learn how to process information, because this is a ketone. Okay, so maybe I'll be explicit here. This is ketone, right? Then you'll notice that after the whole reaction, you get amides. Nitrogen gas is being expelled off. Okay, so they ask you to name the functional group that's formed during this reaction. Of course, the answer is amides. Again, during tutorial, we discussed what's the difference between amide and peptide. I think it's also present in the video for the lecture. So what's the difference? Normally we call the peptide linkage. The peptide is a subset of amide, because amide is a more general term. Peptide, we call the linkage a peptide linkage when it is derived from amino acid residues. So that's from nature. Okay. So other than that, we shouldn't just randomly call an amide a peptide. Yeah, you can call a peptide an amide, but not the other way around, unless it is produced from amino acid residues. Okay, so you need to be sure about that. Then we have a 2-stage synthesis of compound D from B. So D from B, and then make use of this reaction. So keyword is mix use of this reaction. Suggest a structure for intermediate C. You'll notice that what is similar is that B is a ketone, and then eventually you get amide, right? But they introduce an NO2 in somewhere here, okay, into the third position. And keto group is electron withdrawing, so when they introduce the group into the third position, it will be an electron withdrawing condition. So I think that makes perfect sense. So what exactly is C then? So I think you can easily predict that C is actually it has the same structure, okay, except that the NO2 group is now being introduced. And because I have an electron withdrawing group, yeah, so probably I will need to raise the temperature. So corn nitric acid, corn sulfuric acid. Then I just need to write heat under reflux. Okay, so just to ensure that most of the NO2 group gets into the third position. Okay, and then you were told that D can be converted into compound F quite easily. Okay, and then they ask you to suggest the reagent conditions for this reaction. So how do you convert the amides to NH2? Well, I mean, if you look strictly at it, an amide to NH2, probably the byproduct, it's likely to be a carboxylate salt. So this is essentially a hydrolysis reaction. Yeah, and because it's NH2, we probably want to introduce alkaline hydrolysis. So that will simply be NaOH equals heat. Yeah, so we are just introducing alkaline hydrolysis conditions in order to convert to the corresponding phenolamine. Okay, then next, you're asked to draw the structure of the organic products when compound G is reacted with lithium aluminum hydride dry ether. This is one of the learning objectives that is unique to nitrogen compounds. Yeah, so carboxylic acid derivative is now reduced. Okay, so what do you think is reduced to? Of course, for amides, it will be reduced to an amines. So you have to draw out the amines over here. And H, okay, and then with 2 carbons. So remember, there's 2 carbon over here because two carbons. Okay, so remember that. So this is one of the key reactions that is unique to nitrogen compounds. Okay, so with that, I think we have come to the end of the review for nitrogen compound exercise 2.